What if I told you that time is lying to you? Right now, as you watch this video, time is moving slower for your head than it is for your feet. Right now, on the International Space Station, astronauts are aging slightly slower than everyone on Earth. Right now, somewhere in the universe, near the edge of a black hole, a single second could stretch out into 1,000 years. Time feels like the most solid, unshakable thing in your life. The one thing you can always count on, tick, tick, tick. But what if that's the biggest illusion humanity has ever believed? What if time doesn't actually flow the way you think it does? Stay with me, because by the end of this video, you will never look at a clock the same way again. Every single day you trust time without question. You wake up, you check the clock, you plan your life around hours and minutes, and you assume time is the same for everyone, everywhere, always moving forward at the same steady pace. That belief feels obvious. It feels like common sense, but it is completely wrong. Modern science has proven, again and again through real experiments and real space missions, that time is flexible. It bends, it stretches, it can even, in some strange cases, behave in ways that break our basic intuition about cause and effect. This isn't science fiction. This is measured, tested, real physics. Today, we are going to take a journey from the deepest equations of Albert Einstein to the satellites orbiting above your head right now, to the edge of black holes, and finally into your own mind, to answer one haunting question: what is time really? For most of human history, time was thought to be absolute. A king in London and a farmer in China experienced the exact same flow of time. A second was a second, everywhere in the universe, no exceptions. Isaac Newton, one of the greatest scientists who ever lived, built much of modern physics on this idea. In his view, time was like a giant cosmic clock, ticking away in the background of the universe, completely separate from space, completely separate from matter, and the same for every observer, no matter where they stood. For over 200 years, nobody seriously challenged this idea. It matched everyday experience perfectly. After all, your watch and your friend's watch always seemed to agree. But hidden inside this simple, comfortable idea was a problem that almost nobody noticed, until one young scientist working a quiet job in a patent office in Switzerland started asking a question that would change everything. His name was Albert Einstein, and in 1905, he wasn't a famous professor. He was a 26-year-old clerk reviewing patent applications. But in his mind, he was wrestling with one of the strangest puzzles in physics. What would happen if you could travel alongside a beam of light? Einstein realized something extraordinary. The speed of light is constant. No matter how fast you are moving, light always travels at the same speed, about 300,000 kilometers per second. This single fact, when taken seriously, forces something else to break. And that something else is time. Here's the simple version. Imagine two people, one standing still on Earth, and one flying through space at incredible speed. Because the speed of light must stay the same for both of them, time itself has to adjust. For the person moving extremely fast, time actually slows down, compared to the person standing still. This isn't a trick of perception. It's not an illusion. It's a real physical effect called time dilation, and it has been proven by direct experiments. This was the birth of Einstein's special theory of relativity, and it shattered Newton's idea of one universal clock for the entire universe. Time, Einstein showed, is not the same for everyone. It depends on how fast you are moving, and, as he would later prove, how strong gravity is around you. For decades, Einstein's theory remained mostly theoretical, brilliant on paper, but hard to test with the technology of the time. Then, science caught up with imagination. In 1971, scientists conducted a now famous test called the Herfeli-Keating experiment. They placed extremely precise atomic clocks on commercial airplanes and flew them around the world, while identical clocks stayed on the ground. When the flying clocks landed, they were compared to the stationary ones. The results stunned the scientific community. The clocks that had been flying showed a tiny but measurable difference in time, exactly matching what Einstein's equations had predicted decades earlier. Then came an even bigger, real-world proof: GPS satellites. Every GPS satellite orbiting Earth carries an atomic clock. Because these satellites move fast and experience weaker gravity than we do on the surface, their clocks tick at a very slightly different rate than clocks on Earth. If engineers had ignored Einstein's equations, GPS systems would drift off by several kilometers every single day. Your phone's navigation app, the one guiding you to a restaurant or your next destination, only works because scientists corrected for the bending of time predicted by relativity. Right now, every time you use GPS, you are using a technology built on the proof that time is not fixed. Einstein wasn't finished. 10 years after his special theory of relativity, in 1915, he published something even more powerful, general relativity. This theory revealed that gravity itself is not a mysterious invisible force pulling objects together, as Newton had imagined. Instead, gravity is the bending of space and time caused by mass. Massive objects, like planets and stars, actually warp the fabric of space and time around them. This meant something incredible. The stronger gravity is, the slower time moves. A clock on a mountaintop ticks very slightly faster than a clock at sea level, because gravity is slightly weaker at higher altitude. This effect, called gravitational time dilation, has been confirmed using extremely sensitive atomic clocks placed at different elevations, even just a few meters apart. Physicists like John Wheeler helped explain Einstein's equations in ways the public could grasp, famously summarizing general relativity with the phrase, "Matter tells space how to curve, and curved space tells matter how to move." Later, astrophysicists used this exact theory to predict the existence of objects so extreme that time itself would behave in ways that sound almost impossible: black holes. Here is where things get even stranger. Near a black hole, gravity becomes so extreme that time slows down dramatically. If you could somehow watch a friend falling toward a black hole's event horizon from a safe distance, you would never actually see them cross it. From your point of view, their movements would appear to slow down more and more, frozen almost like a photograph, as time for them stretched toward infinity compared to your time. But here's the real challenge scientists faced for decades. How do you prove something this extreme is real when you can't physically travel to a black hole to test it? The answer came through indirect evidence. Scientists studied the orbits of stars near the supermassive black hole at the center of our galaxy, observed gravitational waves rippling through space from colliding black holes, and in 2019, even captured the first ever image of a black hole's silhouette using a global network of telescopes called the Event Horizon Telescope. Each discovery confirmed, piece by piece, that Einstein's strange predictions about gravity and time weren't just imagination. They were describing the real universe. Now let's talk about something that might shock you even more. Astronauts experience time differently than people on Earth. Cosmonaut Sergei Krikalev holds the record for spending more cumulative time in space than any human in history, over 800 days combined. Because he traveled at high orbital speeds aboard the International Space Station, time dilation means he is now technically a tiny fraction of a second younger than he would have been if he'd stayed on Earth the entire time. It's an incredibly small amount, just a fraction of a second, but it's real, measurable, and scientifically confirmed. He effectively traveled forward into Earth's future, just a tiny bit, simply by moving fast enough for long enough. And here's something even stranger: physicists still don't fully understand why time only moves in one direction. In the equations of physics, most processes work perfectly fine running forward or backward. But in our actual experience, eggs break and never unbreak, smoke disperses and never regathers, and people age but never grow younger. Scientists explain this using a concept called entropy, the natural tendency of the universe to move from order to disorder. Because the universe started in an extremely ordered state near the Big Bang, and has been moving toward disorder ever since, time appears to flow in one direction, simply because the universe is still unwinding from that initial, highly ordered beginning. Some physicists believe this arrow of time isn't built into the basic laws of nature at all. It might just be a side effect of the universe's starting conditions billions of years ago. So what does all this mean for the future? Space agencies are already factoring relativity into the design of deep space missions, satellite networks, and ultra-precise timing systems used in global communication, banking transactions, and scientific research. As humanity plans potential future missions toward Mars and beyond, engineers must account for tiny but critical time differences caused by speed and gravity, or our most advanced navigation and communication systems would slowly drift out of sync. Some scientists are even exploring whether extremely precise atomic clocks, accurate to a fraction of a second over billions of years, could be used to detect subtle changes in Earth's gravity field, helping us monitor climate change, underground water systems, and geological activity from space. In other words, our growing mastery over the strange truth of time isn't just theoretical anymore. It's becoming one of the most practical tools in modern science. And on the more mind-bending side, Some physicists continue to study whether the equations of general relativity could theoretically permit shapes in space and time, sometimes called closed time, like curves, that don't forbid time travel into the past in extreme theoretical scenarios. To be clear, this remains deeply speculative and far outside anything achievable with real technology. But the very fact that the mathematics doesn't automatically rule it out keeps some of the world's most respected physicists fascinated by this question even today. So what is time? Really, it's not the steady, unshakable river that Newton imagined. It's flexible. It bends around mass. It stretches near black holes. It moves slightly differently for a person on a mountain than for a person at sea level. It is woven directly into the fabric of space itself, and every GPS signal, every satellite, every precise scientific measurement on Earth depends on us getting this strange truth right. The next time you glance at a clock, remember, that ticking sound you hear isn't measuring some fixed, universal truth. It's measuring your own personal slice of a much stranger, much more flexible reality, one that Einstein glimpsed over a century ago, one that astronauts have now lived through in orbit, and one that scientists are still working to fully understand. Time isn't just passing around you. In a very real sense, you are shaping it, simply by existing, by moving, by being here. And maybe that is the strangest truth of all. If this journey into the nature of time fascinated you, make sure to subscribe to the Voice of Prophecy, because we are just getting started uncovering the universe's deepest mysteries.